All right, we'll get started in another minute. Any problems with submitting today's homework? I probably won't have it graded by Friday, but I should have it graded by Monday. The Monday and Friday assignments are pretty fast to grade. The Wednesday ones take longer. So my goal for Wednesday assignments will be to have them done by the following Monday. In other words, spend my weekends grading. I want to start by discussing something that several people asked me about on the homework, which was the integrals of Gaussians. Gaussian is just a word for any function of the form e to the minus constant times x minus some offset squared. And you were given this. You were given that the integral from minus infinity to infinity of e to the minus x squared dx is square root of pi. Next week, we'll talk about how to derive that. But for now, you're just given that. And so the goal is to use this fact via some use substitutions. So we need to take this integral and somehow turn it into that integral. And a lot of people sat down and started reading up on where the second integral comes from in the first place, thinking that they could use the derivation of this thing to then derive that thing. Well, yes, on some level that's true, but it's true on the fairly trivial level that we just do a u substitution. Let's say we want to get this top integral to be the integral of e to the minus u squared du. So if we say that u is k times x minus x naught, then du is going to be partial u, oops, sorry, there's this button on my stylus that for some reason is not, I don't know how to disable it, so it keeps going off. All right, so du is partial u partial x times dx. Because when you do an integral, you're just adding up a whole bunch of products. The product of a function, the integrand, and some little distance along the horizontal axis. An integral is just a bunch of areas. So if this is our function f of x, then here we have f of x1, and this width is dx, all right? So the dx's are part of the integral. If I want to convert this to an integral of f of u, then there's going to be some du here, some width du, and I'm going to have to figure out what that width du is, all right? So du is the derivative of u with respect to x times dx, or in this case, k dx. And so when I do that, well, this exponent here is the square of this u. But dx is du over partial u partial x. So it's du over k. So what we wind up getting is that this is 1 over k integral from minus infinity to infinity of e to the minus u squared du, square root of pi over k. Any questions on that?
I'm so sorry, Dr. Small. I'm having some pretty slow internet. Are you reviewing the homework?
Yeah, I'm talking about a problem on the homework that several people asked me about in office hours yesterday.
Got it. Thanks.
All right. There's another way we could look at this. Now, strictly speaking, this class is supposed to be purely mathematical, but of course, in physics, you're always talking ultimately about things that you could measure in the real world. So you're talking about things with units. And if we think about it, what would be the units of this integral? If x is in meters, then, well, this integrand is dimensionless. I'll do this in different colors. The integrand, in this case, has no units. This would have units of meters or length. So our answer had better have units of meters or length or whatever units of x are. Now k, in order for our exponent to be dimensionless, the units of k must be 1 over the units of x. And so if the units of k are 1 over the units of x, then what we've got here is the units of 1 over k, which is 1 over x units. And 1 over something is just the original something, so x units. Any other questions? All right, let's do a little more with complex numbers. Last time we were talking about how we could represent some oscillating function, f of t, as the real part of a e to the I omega t plus phi. And this should be omega t. That my handwriting is bad enough in general, it's worse with this tablet. Okay, the real part of that. And that's just if we have a single oscillation. We're going to learn later that we can write functions as combinations of many oscillations as integrals over omega of a of omega e to the I omega t plus phi of omega. So every frequency could potentially have a different amplitude in a different phase times d omega. But don't worry about this if you're a little bit fuzzy on what I just wrote down here. This is just a preview of things coming up in a couple months. For now, let's just take a single piece of that. All right, and we said that the value of this is that we can use it to add 2 oscillations. So let's consider a simple example where we're going to add a e to the I omega t plus a I e to the I omega t. And we're adding 2 oscillations that have 2 different phases, same amplitude, but 2 different phases. If we were to add these up without using complex exponentials, we would have a cosine of omega t plus, well, let's see, what's the real part of I e to the I omega t? That's going to be I cosine omega t plus I times I sine of omega t. I times I is -1. So we're going to have a cosine omega t minus a sine of omega t. And we want to figure out what the amplitude of this is. Now, one way we could do this is that we could try to write this as some sort of a sub s for a sum cosine of omega t plus phi sub s, the phase of the sum. And then we could use trig identities. I don't like using trig identities. It requires memorizing. And don't get me wrong, I'm much more into memorizing than most people are, but I'm still a physicist at heart. I still hated freshman chemistry because freshman chemistry was all about memorizing the fact that the oxidation state of whatever element is +3, except when it's -3 or -5, and sometimes it's -2. And I don't like that. So however much I may be into memorizing, I'm not as into memorizing as a chemist is. So we will not try to memorize too many trig identities. I do want you to memorize cos squared theta and sine squared theta. Those show up so much, you should really memorize those. But there's dozens of trig identities. You know, to a physicist, memorizing a lot means memorizing the orbitals of hydrogen. And there's a formula, so you don't actually have to memorize that many orbitals. To a chemist, memorizing means the whole damn periodic table. All right, so we're not going to do it with trig identities. We're going to do it by adding up the things inside this complex function. So we're going to take this as the real part of e to the I omega t times a times 1 plus I. And we're going to write a times 1 plus I equals as for a sub e to the I phi s. All right, well, let's see. As is the absolute value of a times 1 plus I. Okay, and what's the absolute value of a times 1 plus I? How would we figure that out?
Take the arguments in the complex numbers, square them, and add them together and take the square root.
Take the what?
The arguments of the complex number. So, for example, if it's 1 plus I, it's 1 and 1.
Okay, I know what you meant. Taking the arguments, the terminology here is such that for many people, argument of a complex number means the phase angle. But I know what you meant.
Oh, okay.
The absolute value is going to be of all of that is going to be equal to the square root of the real part squared, a squared, plus the imaginary part, a squared. Because remember that the imaginary part here is a. It's the thing that multiplies a. It's not ai. So that's going to be the square root of 2a squared, or a square root of 2. One way to remember that the imaginary part that gets squared in here is just the thing that multiplies I rather than the I itself. Somebody last night shared a meme with me. 1, I, this is a right triangle, and 0. You see what would go wrong if we put an I there? We'd have the square root of 1 squared plus I squared, or the square root of 1 minus 1, which is clearly wrong. So please don't take this meme and try to use it on your homework. That was just a joke about why you can't square the I. Now let's try to figure out the phase of this, all right? The phase of all of this, the phi sub s. Well, tan of phi sub s is going to be the imaginary part over the real, or a over a equals 1. So phi sub s is 45 degrees, or pi over 4. And we can figure all that out just by using the fact that, well, the real part is a, the imaginary part is A, and then we just have to find a length and an angle. So we could do it geometrically rather than memorizing trig identities. Any questions? No questions? One more chance. Going once, going twice, 3 times, sold. Let's talk about taking the taking the complex conjugate of functions, because the thing that we have to do a lot in physics is integrate f of x, the absolute value of f of x squared, or f star of x, f of x. This is an integral that comes up all the time. It comes up in quantum mechanics, where f is called psi, the wave function. It actually is going to come up later this semester in Fourier analysis. And so let's talk about that. Basically, anytime, if you need to take the complex conjugate of a function, anytime you see an imaginary number, multiply it by -1. For instance, e to the I kx, complex conjugate of that is just e to the minus I kx. You could either remember it via the rule that, well, we just multiply all imaginary numbers by 1, or you could remember that, well, this is cosine kx plus I sine kx. When we take the complex conjugate, we've got to get cosine kx minus I sine kx, which is just e to the minus I kx. Likewise, if we had something more complicated, e to the I k dot r, that's another common way of writing these things. Even though we've replaced the product of 2 symbols with the dot product of 2 vectors, so it looks a little more complicated, people always say to me, so is like if we make the symbol complicated, do we still just multiply the I by -1? Yep, that's a complex conjugate. Multiply the I by -1. I don't care what real numbers are or real symbols are multiplying the I. So that's just, if we take the complex conjugate of that, e to the minus I k dot r. If we had something like x squared plus y squared, e to the I k squared times x squared plus y squared, and this looks a little bit like the integrals we were doing a few minutes ago, but it's not quite the same. Things like this show up in the theory of Fresnel diffraction in optics. And again, there's only one I in there. So if I needed to take the complex conjugate of all that, that's just going to be x squared plus y squared e to the minus I k squared times x squared plus y squared. Any questions so far? Maybe a slightly trickier one. What if we had the square root of 1, f of x is the square root of 1 plus e to the I kx. Well, first of all, we have a rule. We multiply the I by -1. So I could just write it down and assert it, but then I'm going to explain where it came from visually. That's the rule. Now let's think about that. F of x is sitting somewhere in this complex plane. Let's say it's here, right? This is f of x. If we plugged in a different value of x, it could be somewhere else. Actually, no, let's not call that f. Let's call that 1 plus e to the I kx. Let's just say that 1 plus e to the I kx was, except no, that can't be right. let's say that this was 1 plus e to the I kx. Okay, I just realized that 1 plus e to the I kx can't be out here because the real part of 1 plus e to the I kx can't be negative, right? If e to the I kx, hey, let's not put in jokes about massages into the chat. I'll turn off the chat. All right. Saw somebody joking about that. Let's not put that into the chat. All right. Anyway, the real part of 1 plus e to the I kx can't be negative because the real part of e to the I kx is between -1 and +1. All right. And so if it's between -1 and +1, well, when we add 1 to something that's between -1 and +1, we're going to get something between 0 and 2. All right. Now, when we take the square root of something, if I write this as r e to the I theta, when we take the square root of it, well, whatever the length of this complex number might be, we're going to take the square of that length, and we're going to also go down to theta over 2 from theta. This was theta over here. This is theta over 2, right? If I wanted the complex conjugate of f, I would go down to there. Okay, so if I were to take the complex conjugate, I would be going down to there. All right, and in order to find the thing that I had to take the square root of in the first place to get that, well, I'd have to square the length and double the angle. I should really be writing minus theta over 2 here and minus theta, okay? And in order to generate this complex number is just the complex conjugate of that complex number. Any questions?
So it's still just the mirror image on the complex plane. Is that what you're getting at?
Yep, we're still mirroring about the horizontal or real axis.
Okay, brilliant.
All right. Any other questions before we change gears and go to infinite series? All right, infinite series are something that shows up everywhere. I said at the beginning of the semester that our goal is to take functions, break them apart into little pieces. And when we do that, we are summing things up in potentially infinite series. So there are a lot of infinite series. In general, a series is of the form sum from n equals 0 to infinity of u sub n, where u sub n is just the nth term, whatever it might be. Examples, well, the most famous ones are, of course, power series, or Taylor series often called, sum of coefficient times x to the n. Technically, this is a Maclaurin series, and a Taylor series would be offset, but we're not going to deal with that distinction for the most part. It's just a name. We also have Fourier series, often written as sum of an cosine n omega t plus bn sine n omega t. Less familiar series, but we will see them from time to time. You might have something like this, where CL is the coefficient of the L term, and PL is something called a Legendre polynomial. But in all of these series, a vitally important issue is making sure that the series converges. All right, making sure that when we add up all of these pieces, we get something that doesn't go to infinity. So let's start off with one of the simplest series, which you've probably seen before. I'm going to call it S sub n of x. And I'm going to define it as just the sum from little n equals 0 to big N of x to the little n, which is just 1 plus x squared plus all the way to x to the n. Now, you've probably seen this before, but I'm going to do it from first principles, not just because you may or may not remember certain things, but because I want to show the steps and techniques for manipulating a series like this. All right? So let's say that we wanted to multiply this by x. So x times s sub n of x. That would just be the sum from n equals 0 to big N of x to the little n plus 1, because every term got multiplied by x. Now, we're going to do some things where we play with the subscripts, because playing with the subscripts shows up a lot in physics. All right? It shows up a lot anytime you want to manipulate an infinite series. Let's define a variable called j equals n plus 1. All right? So then this is, if j is n plus 1, then whenever n equals 0, j equals 1. And whenever little n equals big N, j equals big N plus 1. So we're going to go from j equals 1 to j equals big N plus 1. And little n plus 1 is j. All right? And so what we've got here is we've got something that has almost all of the terms that are in S sub n, all right? Because this is x plus x squared plus x cubed plus x to the n plus 1, all right? And everything except for the first, we're missing the first term. So we could say this is S sub n minus 1, because it's missing the first term of S sub n. And then it's got one extra term. It's got this last x to the big N plus 1. So x times S sub n equals S sub n minus 1 plus x to the n plus 1. Any questions so far? Something that people sometimes wonder about is, before I define this summing over little n, now I'm summing over j. Well, that's just a name. The important thing is that I'm summing over powers from 1 to big N plus 1, or 0 to big N. What matters is the range of powers, not the names that I temporarily give them. So let's see now if we can solve for S sub n. Because we've got S sub n in here, I'm going to add 1 to both sides and subtract. I'm going to add this to both sides. So the plus 1 goes away. I'm going to subtract this from both sides. And then I'm going to subtract this from both sides. So I'm going to move it over to there. And the result of all that algebra is that there should be a minus sign there. I've got 1 minus x to the n plus 1 equals S sub n times 1 minus x, or S sub n equals 1 minus x to the n plus 1 over 1 minus x. Any questions?
Professor,
Yeah.
on the fourth line from the bottom, we have x of n of x. At the very far right, you have x plus x squared plus x cubed, and you have that equal to s of n minus 1 plus x to the n minus 1.
Yeah.
But you only have it equaling those first three terms. Does it also carry to the x plus n plus 1 term in the top right?
Oh no,
It looks like you cut it
there's
short.
there's supposed to be 3 dots here to indicate that it keeps going, and it finally goes to x sub n plus 1. So yeah,
Okay.
I should have extended this line. So everything on the right here is equal to s sub n minus 1 plus that last term. And by the way, I just realized that the comments in the chat were probably actually not offensive. Sorry if my mind jumped. We've been told to be hypervigilant. You be hypervigilant, interpret things in the worst way. I apologize for, anyway, let's move on. So any other questions on this before I go to the next step? Well, one question we could ask is, what happens if big N goes to infinity? All right, what happens to x to the n plus 1 as big N goes to infinity?
Well, then the whole sum diverges.
Not necessarily. What's 0.5 to a really high power?
0.
Basically, yeah, 0.5 to a really high power. If you take 0.5 and keep multiplying it by itself, you get something smaller and smaller and smaller. Same for 0.8, same for 0.999. You keep getting something that's smaller and smaller and smaller. On the other hand, if I take 5 to a really high power, that blows up. Or even 1.001 to a really, really, really high power blows up. And of course, 1 to the infinity is just 1, but 1 plus something tiny blows up, and 1 minus something tiny goes to 0. So this converges if the absolute value of x is less than 1. And this series itself is actually practical. One place it shows up is in optics. If you've got a wave that hits a multi-layer, or let's take a single thin film for now, N1, N2, N3. Some of the light gets reflected, some of it enters. Of the light that enters, some of it will get transmitted here. Some of it will reflect, make a round trip. Of the light that makes a round trip, some of it now gets transmitted, some of it reflects again. Of this, some of it reflects, some of it transmits, excuse me, some of it reflects. Of that stuff, some of it goes through. And as it keeps bouncing back and forth like that, I'm going to put it on a future homework assignment to work out what it is. But there's a series that shows up there that's equivalent to that. You're basically summing R to a reflection coefficient to the 2m minus 1 times e to the I 2nkd times m from m equals 1 to infinity. And that may not look like the series we just wrote down, but if I pull out that r to the minus 1, I've got r to the minus 1 sum of r squared e to the 2i n k d whole thing to the m. All right, if we call this x, then I've got r to the minus 1 sum of x to the m. So things like that have uses in optics. It's also an example of exponential decay. It may not look like exponential decay because we're used to thinking of exponential decay as something like e to the minus x, and here we've got x to the n. But usually x is the variable. X is the thing that changes as you move out along the axis. Whereas here, we're not moving along the x-axis, we're varying n, right? And as n gets bigger, as long as the absolute value of x is less than 1, x to the n is also decaying. Any questions? All right. So this series is useful for more than just the particular cases where it shows up. It's also useful because it enables us to derive some other series. Let me give you two other series that we can derive from that. We're just going to do calculus on it, right? If I were to integrate dx over 1 minus x from, say, 1 to z, or no, from 0 to z, what would I get? What's the antiderivative of 1 over 1 minus x?
It's the natural log of 1 minus x, but I don't know if that's negative or positive.
Just give me a minus sign. The minus sign comes from the fact if we take the derivative of a natural log, we get 1 over the thing that we took the natural log of. But then we have to take the derivative with respect to x of the thing that we took the natural log of. And the derivative with respect to x of 1 minus x is a minus sign, which will cancel that one, and we're left with 1 over 1 minus x. So this is going to be minus ln of 1 minus z minus ln of 1 minus 0, and 1 minus 0 is 1. And the ln of 1 is 0. So we're left with minus ln of 1 minus z. And because natural logs show up all over the place in physics, sometimes it's easier if you're taking the natural log of something very close to 1, instead of writing out ln explicitly and using that in all of your formulas, sometimes it's just easier to have a series for it and only take the first 1 or 2 terms. Okay, well, how does this help us get a series? Well, I don't have to integrate this thing. This is equivalent to doing the integral of the sum from n equals 0 to infinity, x equals 0 to z of x to the n dx. And I can pull that sum out. And the integral of x to the n is just x to the n plus 1 over n plus 1, evaluated from 0 to z, which would be the sum from n equals 0 to infinity of z to the n plus 1 over n plus 1. Any questions on how I got that? people will often write these series in other ways. Instead of, you'll notice that we're summing over n, but n itself never shows up. It's always n plus 1. So sometimes people will define j equals n plus 1. Then when n is 0, j is 1. And so we can rewrite this as the sum from j equals 1 to infinity of x to the j over j. So people don't like j because there's actually a very good reason to avoid small j. For some reason, in certain branches of electrical engineering, people write little j instead of I. Don't ask me why, they just do. And so they might use n or m or whatever, but it's going to be the sum over some variable going from 1 to infinity of x to that variable, that integer variable, over that integer, sorry. Yeah, I could rewrite it. That would be minus ln of 1 minus x. And yes, I know I was using z up there and x down there. I changed the name, but I didn't change the structure of the equations. And never let it be said that your high school Shakespeare isn't useful for physics. For what's in the name, that which we call a rose would by any other name still smell as sweet. And likewise, that which we call a j would still by any other name be an integer, okay? That which we call z would still by any other name be the thing that we take the ln of 1 minus that variable. Questions?
Yeah, I have a question. Is it the ln of the absolute value of 1 minus x, or is it just 1 minus x?
Just the ln of 1 minus x. But we're going to show, but remember, this only works if the absolute value of x is less than 1, all right? If the absolute value of x is 1, then all bets are off. If x equals 1, well, then we've got minus ln of 1 minus 1 equals minus ln of 0, which is undefined. If we've got x equals negative 1, then we've got minus ln of 1 minus negative 1 equals minus ln of 2. And then the question is whether the series actually converges to that. And that is a very subtle question that maybe we can deal with next time. So if the absolute value of x is 1, or you could say, well, what about I? What if x equals I? Again, there are subtleties that we will deal with next time. But if the absolute value of x is less than 1, then this series works. Other questions? Well, we don't have to just integrate this series. We could also differentiate it. And if we were to differentiate this series, we could take d by dx of 1 over 1 minus x, which is, well, let's see here. The derivative of 1 over something is minus 1 over 1 minus x squared. But then we have to take the derivative of that something that we had the 1 over. And the derivative of 1 minus x with respect to x is minus 1 via the chain rule. And so we've got 1 over 1 minus x, whole thing squared. That's also the derivative of this series. Which is the sum from n equals 0 to infinity of n times x to the n minus 1. Now, the first term in here is, of course, 0. So I could rewrite this. If I have a series whose first term is 0, I can just leave out that first term. You know, subtracting off 0 from something doesn't change it. Taking away nothing changes nothing, except in politics where you can do something that accomplishes nothing, it still makes it look like you took away or gave something, and then people get very happy or very upset depending. But in math, taking away nothing changes nothing. So I could rewrite this as the sum from n equals 1 to infinity of nx to the n minus 1. And then it's usually conventional to make it so that whatever variable you're summing over, n in this case, is the power there. And the reason is not just aesthetics, but that if you want to, say, add or subtract two power series, it helps if all of the terms involve the same power of x or y or z or whatever. That way you can do algebra and arithmetic on the series. So let's say that n minus 1 equals m. Then n equals m plus 1. And so when n is 1, m is 0. And so what we've got is the sum from m equals 0 to infinity. And remember, n is m plus 1, so we've got m plus 1 x to the m, and that is 1 over 1 minus x whole thing squared. Any questions?
I guess the only question that I have was, what was the advantage of changing the subscript?
The reason to change the subscript is so that, I mean, technically, I could then rename m to n again. I could do that if I wanted to. It's not going to matter. But the reason to make this change of subscript, or to go through this change of variables, is so that I am summing powers of n. Because what if later on somebody's got a function like this, 1 over 1 minus x plus 1 over 1 minus x squared, all right? If they want to add those two things, well, that's going to be the sum from n equals 0 to infinity of x to the n plus the sum from n equals 0 to infinity of n plus 1 x to the n. This way, when I'm adding things, I'm adding like terms, all right? So all of this just becomes the sum of from n equals 0 to infinity of n plus 2 times x to the n. All right, otherwise, if I didn't do that, I would have x to the n plus x to the n minus 1. It would be a much clumsier thing to add. Make sense?
I just got really unstable internet. I'll rewatch this. Thank you, Dr. Small.
Okay, in brief, it's just so that that if both of the series are sums of x to the n, then when I add terms, it's easy. Otherwise, I'd be adding x to the n plus x to the n minus 1.
Okay, got it.
Anyone else? Well, so far we've been dealing with one series and the two series that we can derive from that. And there's a few good reasons to focus on these series. One, of course, is that they show up a lot. ln of 1 minus x, 1 over 1 minus x, 1 over 1 minus x, whole thing squared. They show up a lot. Another reason is that they illustrate techniques. There are lots and lots of series out there, and I'm not going to teach you every power series because, for starters, I don't know every power series. Second, for a lot of the power series out there, we could go into a whole bunch of elaborate calculations. And what we would find in the end is after learning a bunch of theory of some function named after a 19th century mathematician, because most functions that are written in terms of series are named after 19th century mathematicians. It was a really good time to do math if you wanted to become immortalized. But at the end of the day, after learning a bunch of stuff about that function, we get, so these things sum to pi. Okay, well that was a great use of 2 weeks of my life. For most practical purposes, you would just look them up in a handbook or look them up on the internet. I'm gonna mostly stick to functions that show up a whole lot, but I will show you in Mathematica what you can do. I'm gonna share my screen. So sums of inverse powers show up a lot. I've defined a function here called the sum of 1 over n to the m. We sum over n, and m is our input variable. And then I'm going to create a table of values for a table of values going from m equals 2, so 1 over n squared, so 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, all the way up to the 10th power. Let's display this thing somewhat nicely, all right? If I wanted, so 2 means I'm summing 1 over n squared. 3 means I'm summing 1 over n cubed, 1 over n to the 4th, 1 over n to the 5th. And those sums turn out to be very simple for even powers. You can relate them to powers of pi. If you want to know why, you'd have to read up on something called the Zeta Function, which is less interesting for the purpose of getting some sums that are powers of pi, and more interesting for understanding some of the deepest questions in number theory. But one little product of that, one little outgrowth of that is that, yes, you can evaluate some series that sum up to like pi to the 6th over whatever. When I need things like that, honestly, I just plug them into Mathematica and ask. For the odd number inputs, again, it's called the Zeta function, but the Zeta function doesn't have any easy answer. So Mathematica just says, well, it's Zeta of 3. If you want to know what Zeta of 3 is, you have to give it another command that says, Zeta of 3 is 1.2. And it shouldn't be any surprise that these outputs become closer and closer to 1. Because let's say I want to sum 1 over n to the 10th. Well, 1 to the 10th is 1. So my first term is 1. Then I add 1 over 2 to the 10th. And 2 to the 10th is about 1,000. So it's a little bit less than 1,000. So I've got 1.0009 something. Plus 1 over 3 to the 10th. Well, 3 to the 10th is huge. So I got 1 over something huge, which is minuscule. So all of these sums very quickly become almost 1, because after the first term, almost everything becomes 0, or very, very close to 0, I should say. So the lesson I want you to take away from this is I'm not going to ask you to memorize Zeta functions. The lesson I want you to take away is that most of these sums, Mathematica knows them, various tables and mathematical handbooks know them. We could go to, it's worth pointing out in a class that studies special functions, the NIST Digital Library of Mathematical Functions. There's this famous book called, it has a name, it's like the Handbook of Mathematical Functions. Every physicist used to own a copy of it. Older physicists still do. It's by Abramowitz and Stegun. At some point, NIST, the National Institute of Standards and Technology, which is responsible for things like maintaining accurate standards of weight and measure, which sounds rather boring, but it has a lot of important industrial use. Their most physics-heavy duty these days is maintaining the accuracy and standards for atomic clocks. NIST is a big employer of physicists and mathematicians. At some point, they put all of this online. So, I would just look in here if I wanted to find various functions and their representations. Anyway, what else do I want to say about that? Okay, so most of these things are not worth memorizing. But while the sum of 1 over n to a power is not worth memorizing, there is something that illustrates a nice technique that I want to talk about. So I'm going to switch back to my other device. I want to illustrate a technique called partial fractions. If I have 1 over a polynomial, like 1 over, oh great, it won't let me do that. Okay, so I got like 1 over n plus a times 1 over n plus b. Well, there is an easier way to express that. And that is to express it as a constant over n plus a plus another constant over n plus b. And it turns out that we can figure out what those constants are by solving a few linear equations. And the reason why that matters is because oftentimes once you break up something like this into something like this, then the sum of 1 over n plus a times 1 over n plus b becomes really easy, especially if a and b are integers or at least differ by integers, and you'll see why. So let's take the case that little a is 1 and little b is 2. So we're going to do the case, let's just do this sum. This is what we want to figure out. This is going to be the sum of a over n plus little a plus big B over n plus little b. All right, well, 1 over n plus 1 times n plus 2 is a over, sorry, it should be 1 and that should be 2, my bad. Okay. Let's get rid of the n plus 1 and n plus 2 in the denominator. Let's multiply both sides by n plus 1 and n plus 2. Well, the n plus 1s cancel there. The n plus 2s cancel there. And everything on the left just becomes 1. So I'm left with 1 equals a times n plus 2 plus b times n plus 1. And a and b are unknowns. We know this is an plus 2a plus bn plus b. Do you see an n anywhere on the left side? I don't know. So if there's no if there's no n on the left side, then an plus bn have to sum to 0. They have to cancel. All right, we're going to cancel them. They tweeted something terrible, and we're going to cancel them. So an plus bn equals 0. Cancel out the n's, and we're left with a plus b. So a equals minus b, or b equals minus a. All right, no n's on the left side, but I do see a 1. So I can conclude that 1 is 2a plus b. And b is minus a, so that's going to be 2a plus minus a equals a. So a is 1 and b is minus 1. Any questions? All right, well, here's the beauty of it. I've got the sum from n equals 0 to infinity of 1 over n plus 1 minus 1 over n plus 2. All right. I've got each term minus the next term. Okay? Can you see how this is just the next term here? So the next term is all, the first half, the second half of this term is the first half of the next term. So do you see how intuitively there's going to be some cancellation coming up?
Right.
Yeah. Terms are canceling each other. They're all tweeting terrible things. I know that joke will get old very fast. Oh, I thought there was something. It looks like there's, okay, I was trying to erase something. Anyway, let's do this explicitly by changing the subscripts. So let's say that j equals n plus 1 and L equals n plus 2. So this, let's see here, when n is 0, j is 1. So we're going to have the sum from j equals 1 to infinity of 1 over j minus the sum from, well, when n is 0, L is 2. Sum from L equals 2 to infinity of 1 over L. And I could write this as 1 over 1 plus the sum from j equals 2 to infinity of 1 over j minus the sum from L equals 2 to infinity of 1 over L. So what I've just done here is I've taken, first I took this complicated expression, 1 over n plus 1, 1 over n plus 2, and I broke it up into two simpler pieces. And this trick isn't just used for series, by the way. It's also used for integrals. Imagine that instead of wanting to do a summation, I had to integrate this. That this was x plus a times x plus b in the denominator. Well, I don't know how to do that integral. But I know how to integrate 1 over x plus a, and I know how to integrate 1 over x plus b. So this partial fractions trick works for a lot of things besides these sums. That's the other reason why I'm talking about it. It's not just to add one more series to your inventory, but to add a trick that you can use for multiple problems. So I take this complicated expression. I turn it into something simpler. And then I note that I could really write each of these terms as the exact same thing, just with different starting points. Same thing being summed, just with different starting points. One of these starts from 1, the other starts from 2. And then I take the thing that is different only because they have different starting points. I say, all right, I'm going to isolate the thing that's different, the thing that comes from this first series starting one term earlier than the second series. That's 1 over 1, or 1. And then I've got these two other series that both start from 2. And these two series are the same. Again, they have different names. Here I called the integer j. There I called the integer L. But what's in a name? That which we call j would by any other name still be an integer. So these cancel. And we're left with 1. Questions? Questions? Okay, so far I've been showing you tricks. but there's no guarantee that a series will converge. If all you're doing in a project is just taking some function that's already known and simplifying it because you've got a bunch of logs and cosines and whatnot, and you want to simplify things, well, then maybe you just plug and chug some known series. But if you find yourself learning a new computational technique or trying to develop a new technique for solving a problem, then the convergence of a series matters a lot. One of the projects I have on my back burner that I've worked on over the years, and I hope to someday finish it, is a project for solving Maxwell's equations in a rather unusual case that involves waves traveling in two different types of materials. And for solving this problem that involves waves traveling in two different types of materials, I have to write down a bunch of special series involving Bessel functions and Legendre polynomials. And I have to make sure that these two series are converging to the same value on both sides of a boundary. So convergence tests do matter, and we're going to start talking about them. We're not going to finish them today, but I want you to read through the book chapter. I think it's chapter 5 or whatever it is. I don't have.
Chapter 4 for those who are wondering.
Yeah, chapter 4, sorry. Read through chapter 4 on infinite series, on convergence tests, and then we'll review some of that on Monday. This Friday, we're going to be doing activities that involve complex numbers and oscillations. All right, the sum of u sub n from n equals 0 to infinity. A necessary condition is that un goes to 0 as n goes to infinity. Otherwise, you're adding a constant plus a constant plus a constant plus a constant. You're adding something that's definitely non-zero and is bounded by something non-zero. And you're just adding up the same thing, an infinite or almost the same thing, an infinite number of times. That's infinity times almost the same thing. That's going to be infinity. So this is necessary but not sufficient. So what are some tests to try to find sufficient conditions? Well, one is a comparison test. Say we know that the sum of v sub n converges. And indeed, we know that if v sub n equals x to the n, the absolute value of x is less than 1, we have a convergent series. So one thing you could do is compare the series that you have with a series that you know to be convergent. And if the absolute value of u sub n is less than the absolute value of v sub n, at least for the later terms, then they converge. Now, why am I saying for n bigger than some big N? Well, let's put little n on the horizontal axis and un and vn. And so in red is v sub n, the thing that we know converges. And in blue is u sub n. Now, we don't care if initially u sub n is bigger than v sub n. The first few terms, u sub n could be whatever. As long as it's finite, we don't care. If you have a few big terms and then everything else rapidly converges, great. You know that you have something whose value is dominated by those first few terms. We just care that eventually u sub n becomes less than v sub n. And this is the place where from here on, u sub n is less than v sub n. And you'll notice that I showed that initially being bigger, then smaller, then bigger again. I don't care if they swap off for a while. I don't care if sometimes U sub n is bigger for a while and sometimes V sub n is bigger. All I care about is knowing that after some initial weirdness, once we get out towards infinity, U sub n is always smaller than V sub n. That way I know it converges. This is not a necessary condition for convergence. There are other ways to converge, but it is sufficient. This would be called the comparison test. Another is called the ratio test. Where you say, is the absolute value of U sub n plus 1 over U sub n less than 1? Hopefully, by the way, you saw some of these tests back when you were taking calculus and you did infinite series. I regard this as a review. I'm not here to give all the proofs, but to review what I think is most important and worth remembering. And to give you an intuitive idea for why this matters, this is kind of like the comparison test in that let's consider the series that we know converges. The sum of x to the n, absolute value of x less than 1. Sorry, x to the n, not x sub n, my bad. Well, here U sub n plus 1 over U sub n is x to the n plus 1 over x to the n, or just x. And we know that this series converges if the absolute value of x is less than 1. And so if we have some other series where that ratio is less than 1, again, we know that that other series is decaying even more rapidly than a series that we know to converge. All right, because we know that the sum of 0.99 to the n converges. Converges slowly, but it converges. So if somebody else gives us some other series and the ratio of two terms is less than 1, well, it's that maybe that ratio even is less than 0.99, then we know that everything is decaying more rapidly than the simple series that we know to converge. Questions?
I have a quick question about the comparison test. So you mentioned that the series has to be finite. Can you explain that further, please?
Oh no, the series doesn't have to be finite. The region, you could have, let's say that the series we're trying to figure out is U, and we know that V converges. U could be bigger than V for some finite number of terms. We don't care if initially U is often bigger than V.
Okay.
At some point, I mean, the whole issue of convergence is not what happens with a few terms. Nobody cares if you add up a few big terms. Add up a few big numbers, you still have a finite number. It's a big finite number, but it's finite. The whole point of here is to make sure that it doesn't go to infinity, all right? So if there's a finite number of terms where this unknown series, this series U, whose properties we're still trying to figure out, if that's initially bigger than V, who cares? As long as once we get out towards infinity, that there is an infinite number of terms where U is less than V, and only a finite number of terms where U is greater than V. Then we know it's going to converge.
Okay, thank you.
One more important test is the integral test. Right? The integral test is that if the integral from some number at big N to infinity, f of n dn is finite, then the sum of f of n from n equals 1 to infinity, or big N to infinity, is finite. You know, actually, I'm going to rewrite this more simple. I'm going to rewrite this in more practical terms. Why was that not erasing? Who knows? Okay. Because imagine we've got some function whose integral is infinity. This is f of n. Then all of this area under the curve is just the integral. Now the series would be a little bit different, right? The series would be, well, this is 1, this is 2, this is 3, this is 4. So here you would have f of 1 times 1. The red area would be f of 1 times 1. This red area would be f of 2 times, again, 1, because you're thinking, well, it's 2, but the width of this is 1. So f of 2 multiplied by 1, f of 3 multiplied by 1. All right? And all of these areas, these red areas, this boxy region that I've marked off, are less than the area of the curve, area under the curve. So the sum of these red areas is less than the integral of f of n dn. And if this was finite, if that integral is finite, then this must also be finite. So the last thing in 1 minute, let's say that we have the sum of 1 over n to the m. Does it converge? And you may be saying, well, of course it converges. We just typed it into Mathematica and it converged. Sure, for the cases I showed you. Does the integral from 1 to infinity of dx over x to the 1 converge? What is that integral? Anyone?
The natural log.
Yep, that is ln of x evaluated from 1 to infinity, which is ln infinity minus ln of 1, and ln of infinity is infinity or undefined. So that doesn't converge. So we can immediately conclude that the sum of 1 over n from n equals 1 to infinity, that blows up. On the other hand, I showed you that Mathematica can handle the sum of 1 over n squared. And that was pi squared over some integer, something finite. And the integral of dx over x squared from 1 to infinity is minus 1 over x evaluated from 1 to infinity, is minus 1 over infinity, that's 0, minus negative 1 over 1. Minus negative is plus. So this is 1, this is finite. So the sum of 1 over n squared converges and the sum of 1 over n diverges. All right, we're out of time. On Friday, we'll have 2 sessions where you'll be going over an activity that involves complex numbers and complex oscillations. Over the weekend, read up on the convergence tests and read up on Taylor series, particularly Taylor series of common functions. And we will discuss some of those Taylor series and what they show about the convergence tests on Monday. Have a good day.
Thank you, Professor Small.
Thank you.
You're welcome.
Thank you.
And by the way, I realized that
Thank you, Professor.
I misunderstood something about a joke. This is why I like the fact that there's a Discord channel. If you want to tell jokes that I may or may not get, do that on some channel that no one's required to participate in. You know, if you're required to participate in the Zoom chat, so you show up to the Zoom chat, you're required to participate in the Zoom lecture. You show up to the Zoom lecture, the chat has questions about the class and maybe some very low risk jokes. Nobody has to worry. You want to tell jokes that I might misunderstand because I'm being paranoid because my employer requires me to be paranoid. You put those in the Discord. I don't see them. Anybody who wants to sees them. Anybody who doesn't want to doesn't. It's all good for everyone.
Dr. Small, just a quick question, and I hope
Yeah.
that you can hear me.
Yeah, I hear you.
You know, my internet was super unstable today, and so I missed out huge chunks of the lecture. Will this be posted after class?
Yep, as soon as I disconnect from Zoom, it's going to start processing it into a video that I can post on YouTube, and it'll be on YouTube sometime in the early afternoon.
Okay, thank you. All right, thanks so much. See you soon.
No problem. Not quite.
Professor, can I ask you a question?
Of course.
I had my orientation with you before the semester started, and I'm not sure if I'm supposed to be reaching out to an advisor or if they're supposed to be reaching out to me.
You normally contact the advisor, but you don't have to
Oh,
worry
okay.
about that for a few weeks yet, because class registration doesn't start until sometime in October. Hang on, my little tab.
Oh, okay. Awesome. Thank you. Have a nice day.
You too. Ewan, Lee, any questions? I see 2 people logged in who are not responding. Do you have any questions before I disconnect? Okay, seeing no response, I'm disconnecting.